All right, for our first example here, we're going to parameterize a sphere with radius of 4. So before we actually go to the parameterization, let's just write down a couple of things that we need to recall. We're going to recall our conversions in cylindrical coordinates. Remember that x is r cosine theta, y is r sine theta, and z is still just z. And in spherical coordinates, x was rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So we're going to focus obviously on the spherical. It is a sphere. Now remember, when we parameterize this, we're parameterizing the surface of the sphere. We're only parameterizing the surface, which means that the radius, and it says it specifically here, our radius or our rho is 4. It's always 4. So we're taking this thing from x, y, and z down to only phi and theta. Those are the only things that are going to vary. Rho is going to stay constant. So just the surface of the sphere. So again, rho here will be constant, and rho is 4. So x is going to be 4 sine phi cosine theta. Y is going to be 4 sine phi sine theta. And z is 4 cosine phi. And if I wanted to write this, before we take a look at it, if I wanted to write this as an actual vector valued function of r, we would write this as r of, and it's a vector, theta phi. r of phi theta. I said it backwards. And of course that would just be rewriting it again, 4 sine phi cosine theta, 4 sine phi sine theta, 4 cosine phi, and that would be your vector valued function r of phi theta. Let's take a look at this thing in Calcplot 3D. Alright, so as you can see here, I've defined my x. Now again, excuse me, we have to use u and v here because that's what Calcplot 3D has. But the u is going to represent our phi, and the v is going to represent our theta. So u is 4 sine phi cosine theta, and you see that y is 4 sine phi cosine theta, and that z is 4 cosine phi. Now I'm going to let the phi go from 0 to pi, because remember phi, which is the angle of bloom from the z-axis down, can only go up to pi. It can't go past that. If it does, it's just going to overlap itself, so it doesn't make any sense. And then our theta is going to go from 0 to 2 pi to create the entire sphere. And again, this is just going to represent the surface. And there you have it. Now, of course, like we did before, how do I know that the inside of that isn't completely filled in? Well, let's go ahead and take a look at it. We're going to cut out a wedge of this thing. So we'll go from 0 to 3 pi halves, I think should be sufficient again. 0 to 3 pi halves. That should be sufficient so that we can see that the inside of this sphere is actually hollow if we limit it. So let's take a look now. And there you go. You can see the inside of that sphere is hollow. Kind of looks like a tennis ball that a dog has chewed off the edge of it, or the quarter of it, or something like that. But there you go. There is the surface area of that sphere parameterized. All right, for our second example, we are going to parameterize the cone x squared plus y squared equals z squared. And one of the interesting things about this is, well, obviously it's a cone. It is not a sphere. It is not a cylinder. So we can actually parameterize it using either one. So if we were just to kind of sketch a cone, something like that. I'm going to redraw that. That just doesn't look that good to me. That's better. At least I hit the top of it. And this cone, because of the fact that it's got the x squared plus y squared equals z squared, technically is going to go on in both directions. Something like that. Man, I'm just not really doing those circles very well here. Still not great, but you get the idea. We're going to parameterize this both ways. We're going to parameterize it in both spherical and cylindrical, and we'll show, going back to the calc plot, that it works. It's the same thing either way. So let's take a look at spherical first. So one of the things is it's a cone. So the one thing that doesn't change here is the angle of Bloom. No matter what, the angle of Bloom is always going to be the same. Even if we were to project it down here, the angle of Bloom is exactly the same distance away all the time. So the angle of Bloom here, or your phi, is pi fourths in this case every single time. So when we go to write this, the phi part is going to be constant. It's always pi fourths. Rho, however, changes. Right? Rho goes from here, that's one thing, then it's here, that's another thing, then it's here, then it's here, and so on. I'm going to erase those, but rho does change. It changes as this thing gets bigger and bigger, and it's going to keep on going forever. And the theta part has to vary from 0 to 2 pi so that the cone goes all the way around. So I'm actually going to have a function here in spherical of rho and theta. That's going to be my r. It's going to be a function of rho and theta. So let's go ahead and write these. So x is going to be rho, that changes, sine of phi, but remember phi is constantly pi fourths here, cosine theta. And then y is rho sine of pi fourths, sine theta, and then z is rho cosine of pi fourths. So again, phi is constant, and the function here that we would get is some kind of r of rho theta. And so that would be written as well, we can actually figure out what sine of pi fourths is, so we don't have to write it as sine of pi fourths, although you can. It's technically not wrong, but sine of pi fourths is root 2 over 2. So the x value would be root 2 over 2 rho cosine theta. The y value would be root 2 over 2 rho sine theta. And then cosine of pi fourths is also root 2 over 2, so it's just root 2 over 2 rho. And we could define it like that. And again, I'll go to calc plot and show you that. But now we're going to parameterize this thing, and we're going to do it in cylindrical. And we're going to show that these two things, cylindrical, are exactly the same when we go to the calc plot. So now in cylindrical coordinates, remember that's just x equals r cosine, y equals r sine, and z equals z. Well, it's not really going to change that much. X here, oops, did not change that. I was thinking I would. So x here is just going to be r cosine t. Y is going to be r sine t. And again, remember, t is basically your theta that goes all the way around. It has to. R is like your radius. That's your rho, basically. It has to go out to the edge, so it's constantly changing. And the z part, well, the z part is usually some z, but we're going to have to figure out how we're going to have to define z in order to make this thing work. Well, z, if you actually look at the original equation, is defined, well, z squared is defined as x squared plus y squared. So z squared is x squared plus y squared, but x squared is going to be r squared cosine squared t. Y is r sine t, so that's going to be r squared sine squared t. And of course, factoring out the r squared, you would just get r squared times 1, because you'd get cosine squared plus sine squared left over. And so that just means that z squared equals r squared, or z equals plus or minus r. And we're really only interested in the positive r as far as that's concerned, as far as writing it. But we do have to take into account, and we'll show this, that r is going to have to go from negative infinity to positive infinity. So our parameters, oh, I forgot to write the parameters on the other one. I'll go back and do that in a second for the spherical. Our parameters for this one is that t, which is basically your theta, has to go from 0 to 2 pi. And r, which is your radius, technically just goes to infinity. But in order for us to include the bottom part of the cone, we'd have to go to negative infinity, as again, you can't really have a negative radius, but that just indicates it goes in the negative direction. So that's your parameters, that's your domain. And then I'm going to go back and I'm going to write the domain for the spherical, because I left that part off. So the spherical domain, theta, was in between 0 and 2 pi. And then rho, once again, we had to let go to infinity. And in order to get the bottom half of the cone, we'd also have to let rho go to negative infinity. All right, last piece here I will do real quick, and then we'll take a look at this on CalcPlot, is I'm going to go ahead and just write out the r. So this would be an r of, what do we say here? We've got r and t. R of r and t, I guess, is going to be the way you would write it. So that's going to be r cosine t, r sine t, and we decided that z is going to equal r. We don't have to use the plus or minus because of the fact that r is going to vary from negative infinity to infinity. All right, let's take a look at this on CalcPlot 3D and show that both of these things actually give us exactly the same cone. All right, as you can see here in my in the second box here, I've got x defined in spherical first. I did u cosine of v sine pi 4, so I put the sine at the end. Not that that makes any difference as where it is. And again, I could have written the sine part as root 2 over 2. I just went ahead and defined it as sine of pi 4 because that's how we started. The y part is u sine v sine of pi 4, and then u cosine of pi 4. Now, we would normally have let the rho part again go to infinity, but in order for us to be able to see it here on the graph, I stopped it at 3. So let's go ahead and take a look, and there you have your cone. And as you can clearly see, it's just the outside of the cone. It's nothing filled in on the inside there. It is just the outside piece. But of course, that's only the top part of the cone. And the reason for that, of course, is because I did not let u go negative. So let's go ahead and change that. Just for symmetry, we'll go to negative 3. And then we'll go ahead and redraw it. And there you have the top and the bottom half of the cone. Now, just to make sure that you guys understand that this is exactly the same thing as if we did it in cylindrical, I'm going to go ahead and take off that graph. The one at the bottom here is cylindrical. There's your r cosine t, r sine t, and z equals r. Again, I just went from 0 to 3 and 0 to 2 pi, the 0 to 3, just so we can show and it's just going to give us the top, but it's exactly what we saw before. And then if I wanted to change that to show the bottom portion of it like we did, go from negative 3 to 3 for symmetry, and there you go. There is your cone. Again, it is just the surface area of the cone.